All right, today we're going to tear down one of the most important pieces of tech in all of modern electronics, the microstrip antenna, or as a lot of people call it, the patch antenna. It's this beautiful piece of engineering that's both super simple and has a massive impact. We're going to break down exactly how it all works.
You know, you probably can't see one right now, but I guarantee you're using one. This thing is the unseen engine of our wireless world. I mean, it's literally in every mobile application. It's crammed into your phone, it's up in satellites, it's everywhere, all because it's tiny, it's cheap to make, and it's unbelievably versatile.
So here's our game plan for this explainer. We'll start with the basic anatomy of the patch. Then we'll dive into the physics, how it actually sends out a signal. After that, we'll get into the fun stuff, the design knobs an engineer gets to turn to tune its performance. And finally, we'll see how it stacks up in the real world and where it's being used. Okay, first things first, let's deconstruct this thing. You're probably going to be surprised by just how elegantly simple its core structure really is. At its heart, it's basically a three-layer sandwich. On top, you've got the radiating patch. That's a thin piece of metal, usually copper, and it does all the heavy lifting of sending and receiving signals. It sits on a dielectric substrate, which is really just a fancy term for an insulating material. And that layer separates the patch from the bottom layer, a big slab of metal called the ground plane. And that's it, 3 simple layers. So how do we turn that simple sandwich into an engineering blueprint? Well, looking at it from the top, we care about 2 critical dimensions, its length, which we call L, and its width, which we call W. Then, if you look at it from the side, you've got the substrate height, H, and its most important property, the dielectric constant, or epsilon R. Seriously, these 4 things, L, W, H, and epsilon R, are the absolute keys. Everything else about the antenna's performance flows from them. Okay, so we know what it looks like, but how does this simple metal patch actually launch electromagnetic waves out into the world? Let's dive into the physics. The real magic happens right at the edges. See, the electric fields between that top patch and the ground plane, they don't like to stay perfectly contained. At the edges, they kind of fringe or bulge out into space. And here's the crucial takeaway. The antenna radiates almost entirely from these 2 slots along its width, W. The sides along the length L, barely any radiation comes from there. It's this fringing that flings the signal out into the air. So we've got the basic mechanics down. Now for the really cool part. How do we turn this knowledge into a practical design? Just think of those physical dimensions, L, W, and H, as the control knobs an engineer can tweak to get the exact performance they need. This flowchart is the perfect roadmap for that. On the left, you've got our physical inputs, our control knobs, length, width, height, and that dielectric constant. And on the right, you see what they directly control, the performance characteristics, like frequency and bandwidth. Let's break down the most important of these connections. First up, the big one, operating frequency. This is almost completely controlled by the length of the patch, L. The rule of thumb is that for the best radiation, you want L to be about half a wavelength of the frequency you're aiming for. The formula here proves it. See how the resonant frequency, F0, has L in the denominator? That just means it's inversely proportional. So a longer patch gives you a lower frequency, a shorter patch gives you a higher one. This is your main tuning knob.
Now the width, W, is just as important, but it's kind of like a multi-tool. It does a few different things. First, it controls the input impedance. As you can see, a wider patch gives you a lower impedance. Second, it affects bandwidth. A wider patch can handle a wider range of frequencies. And finally, remember how radiation happens along the width? Well, a bigger W means you have a bigger radiating area, which pumps out more power.
Next is the substrate height, H, and this one involves a classic engineering trade-off. It's a balancing act. If you look at the graph, as you make the substrate thicker, your radiation efficiency and bandwidth both go up, which is awesome. But there's always a but. If you make it too thick, you start wasting power on these nasty things called surface waves that get trapped and go nowhere. So what's the sweet spot? The general rule is to keep the height less than about 5% of the wavelength you're working with.
This all leads us to a really critical, real-world engineering problem. Your signal comes in on a feed line, and that line almost always has an impedance of 50 ohms. To get all of that power into the antenna and not have it reflect back, the antenna's input impedance also has to be 50 ohms. So how do we nail that perfect match?
The solution is actually pretty genius. It turns out the impedance on the patch isn't the same everywhere. It's really high at the very edge, and it gets lower as you move toward the center. So engineers use this clever trick called an inset feed. They cut little notches and move the connection point inward,
basically hunting for that one perfect spot where the impedance is exactly 50 ohms. It's a simple and elegant way to make sure no power goes to waste.
Now, for those of you who really want to see the math behind the magic, these are the formulas for the radiated electric field. Don't worry, we're not going to derive them. Just look inside the brackets. See, W and L, our width and length, are right there in the core of the equations. This is the mathematical proof that what we've been saying is true. The physical size you choose on your circuit board directly and predictably creates the invisible radiation pattern out in space.
All right, we've covered the structure, the physics, and the design knobs, so let's put it all together and give this antenna a proper real-world performance review. What's it good at and where does it fall short? So here is the final engineering scorecard. The advantages, the pros, are huge. You can just print them onto a circuit board, which makes them insanely cheap, tiny, and lightweight. But you've got to know the cons. A basic patch antenna has a really narrow bandwidth and pretty low gain. It also only radiates in one direction, into a half plane, and it can't handle a ton of power. Oh, and you always have to be on the lookout for those pesky surface waves we talked about.
But even with those limitations, the advantages are so powerful that this antenna is, well, it's absolutely everywhere. Just look at this list. It's in the smartphone in your pocket. It's in the satellites giving you GPS. It's in your Wi-Fi router, in advanced fighter jets, and even in cutting-edge medical devices. Its impact is just massive.
So, to boil it all down, if you remember nothing else, remember these 4 things. 1. It has a dead simple form, just a patch, a substrate, and a ground plane. 2. It has a clear function. It radiates using fringing fields. 3. It gives engineers direct control through its dimensions. And 4. All that adds up to a broad, undeniable impact on our connected world.
And this brings us to one last big question to think about. This antenna's design is all about balancing trade-offs. As we push toward things like 6G and beyond, we're going to need higher frequencies and way more bandwidth. So how will this elegantly simple design have to evolve to meet those incredible demands? That's the challenge that engineers are tackling right now. Thanks for tuning in.